No key. Sorry. Oh, good. So, could we start? Hi, everyone. So, my name is Andrey Zubkov. I hope almost everyone is familiar with me. In my master, today I would present you my master thesis, my master work in general, because obviously not all the work that I did during the masters would enter my diploma. So today we would talk about silent speech recognition on electromyographic signals. Mostly this topic is really old. It was kind of initially researched in 1980s or something like this. But all the way through this 40, almost 50 years, scientists trying to research silent speech recognition on enclosed corpora. So they take kind of limited command set and then try to recognize it. And actually, even in the end of the 90s, it was already successfully recognized. I mean, command sets, about 20 commands, were successfully recognized and distinguished with 95+% accuracy. So there is almost no room to improve it. I mean, just apply this technology somehow, like alter ego that I would. Could you please next slide? Like I was mentioning previously, did. So mainly for those who is not familiar with what are electromyographic signals, how we do in general the silent speech recognition, electromyographic signals are the signals of our muscles that we could take from the source of the from the surface of our skin. And actually, when we want to talk something, to tell something, when we mentally spell in the words, even in this case, when we don't say it loudly, we still generating the muscular activity. So because of this speaking habit, as it is called in electromyography, because of this, we could detect silent speech even when person is not moving his lips at all. So there is no movement, you just thinking, and we see the result. So yeah, next slide, thank you. What we want to detect the silent speech for. Actually, there are a lot of applications. Even the NASA kind of provides the document with the patent that they've shown in 2017 approximately, where they list kind of 30 or 40 applications that they were thinking of already in 2017. But my work is mainly focused on 4 things. There are here listed. First is noisy environment speech recognition, because obviously when you are in the construction plant, you probably won't be able to detect your speech at all with kind of usual microphones or something. Second is surgical intervention support when patient is not able to speak during the operation. For instance, if the surgeon would cut your throat or something like this, I don't think you would like to move your throat at all. So you would think of the words and the surgeon would have a feedback from you. So it is a human machine and human-human interfaces, especially for Asian countries where there are a lot of people, where there is almost no room to talk in private. And in this case, you would just think of something and another person would be able to receive your message even without saying loudly anything at all. Yeah, this is also the fourth thing. And the third thing is the same conversation from youths, because if people couldn't talk, it is a very good idea to let them this ability with these auxiliary devices. Next slide. Yeah, that's actually how the hardware setup looked like for collecting the data set. Mainly the work of master thesis is related to distinguishing silent speech phonemes, which is quite usual task for automatic speech recognition in general, but for silent speech wasn't done by anybody till now. So yeah, as you could see, we've taken the EEG electrodes, which are more sensitive than usual EMG electrodes, because obviously we don't want to prove that we are not trying to improve the technology of detection something with cheaper hardware or something. We are just trying to prove that we could to distinguish these phonemes properly at all. So yeah, we taken the best hardware we were able to find, and actually yeah, build such a mask so that person could wear it. Yeah, and we detect their, next slide, yeah, already, detect their behavior, their silent speech. Yeah, mainly which are the silent speech recognition problems you could see here on the slide. Mainly it is first that there are very small number of data sets and very small number of data at all, because the only free data set, more or less big size, is 1.3 hours. Yeah, this is EMG UK, and there are closed and enclosed data sets that are not available for researchers, so it would be a problem. And as you may know about automatic speech recognition, usually there are kind of thousands of hours of initial data set marked down properly to train even the hybrid model for automatic speech recognition, without saying about end-to-end approaches, which require multiple times more, kind of 100,000 hours. And obviously on 1.3 hours data set, it's almost impossible to train kind of proper model for open vocabulary silent speech recognition. Yeah. Oh, sorry. Okay, let's move further. Yeah, mainly during my master's, I've conducted another research on recording the data sets on silent speech. So I've created the technology with Anrew that is sitting here for recording the data markdown for EMG on loudly saying words, which was proven by M1, thank you, my slides, that it won't affect the quality of final model if we do loud speaking things and convert them to markdown. Yeah, thank you. So mainly we could go further. This solution was described in model on in paper on SSDSE. Yeah, next slide again, and next slide. Yeah, so you could read it in more details. And finally, the research I've conducted for my master thesis was the distinguishing of silent speech phonemes. We've taken actually about 6,000 of repetitions of phonemes, of 42 phonemes. It was more than kind of 150 repetitions for every of a kind. And we actually wanted to achieve the same score as we get in automatic speech recognition for audible speech. It is about 31 to 32% for hybrid models, which use acoustic things under hood. So actually, session-wise and speaker-wise, we achieved less than 30% phoneme error rate, which is just awesome, especially considering that this model could be trained in kind of seconds. So after that, next, please. Yeah, after that, we've conducted kind of 5 sessions, and on 4 speakers. And we find out that all the way through this big data set from 5 sessions, we obtained 35% of phoneme error rate, which is a little bit worse than the 32% of phoneme error rate for audible speech recognition. But audible speech recognition values are obtained from dataset on 39 phonemes. Please, next slide. And if we can scale our error to the 39 phonemes from 42 phonemes, which we used, we would obtain kind of almost the same 32.5, even in the worst case scenario, if it would just kind of decrease number of outputs for our model. So if we transfer it to word error rate, kind of audible speech recognition models, usually hybrid models, achieve 12% on big data sets. And for our model, it must be with language model over this acoustic one. It should be around 15%. Please, next slide. Yeah, here you could see the number of literature. And what I want to say in the final step, mainly for the PhD, I really plan to go for collecting the big data set with the method I've described in paper, and collect kinda at least 50 to 100 hours of records, because now it is 200 minutes almost, even a little bit more. So, and probably even in 2 or 3 years, which I assume would be enough time for collection of 50 to 100 hours of data, model for silent speech recognition, possibly usable for kind of daily usage, could be achieved and could be done, could be created. So yeah, if you have any questions, I would be really glad to answer them. Thank you all. So any questions, guys? I really welcome. Yep, sure.
Thank you for your talk. Could you please tell what was the format, the actual format of the data set? Were the phonemes parts of real words? And how long were the words or the phrases?
Thank you for this question. It is actually a very important thing. And that's actually the weakest place of the work in general, because in traditional approaches, we use the phonemes that are really a part of words or a part of commands and so on. And in this work, it is completely vice versa. It is only the phoneme that was recorded separately out of any words, out of any context. From one side, it could lead us to, we could use longer periods for detections of this phoneme and so on. But really, in kind of real world scenarios, even when we use acoustic models, when we split in the phoneme for kind of short parts, we still considering the previously obtained parts and previously predicted parts for prediction of final value of a phoneme that we want to give to our kind of language model or something. So mainly this from one thing is an advantage for our approach, and from other side it is disadvantage. This is why I think it is still okay, and we could consider our results as kind of significant. But yes, to move to real model, obviously usage of all complete words would be necessary. Yeah, thank you. If it was the answer, yeah, good.
I have two questions in one notion. Maybe I start from notion that it will be good for pre-defense and for defense of your work to shrink your presentation, because a lot of introduction and small number of results. And for these two questions, what is your contribution to the science in this field? And second, I didn't mention, have you listed your publication?
Yep.
Yes?
Yep, sure.
Okay.
So about the first question about the contribution, actually previously in any work you could find on silent speech recognition from either EMG or EEG or any other source, you could find that there was no works for open vocabulary silent speech recognition at all. And the second thing is that nobody proved that it is possible kind of in future or with other approaches or something. So this work mainly is about the proof of concept that we could go from common set recognition to open vocabulary speech, silent speech recognition with no kind of preventions, with no obstacles from the phoneme recognition, kind of use the hybrid models with no need for kind of end-to-end models even that would require kind of multiple millions of investments to obtain kind of hundreds thousands of hours. So this actually the main contribution, that if somebody would want to research the silent speech in future, he would find this article and not article, but the master thesis, and he would see that, okay, it is mainly possible to distinguish phonemes properly.
Okay, thank you.
Mm-hmm. Any other questions? So, yeah, thanks a lot. I would love to. Sorry.
Как-то у меня точно так. Ладно. Good afternoon. My name is Yakovenko Olga, and today I'm going to present you my talk on convolutional variational autoencoders for audio feature representation in speech recognition systems. So, first of all, the outline of my talk. First, I will talk about variation autoencoders in general. Then I will review what works were done before this work on variational autoencoders and audio feature representation. Then I will talk about what was the problem that we posed, what was the task for us to solve, and in the second section of experiments, I will review how the variational autoencoder was trained to represent our set of audios, and also I will review the speech recognition results with the usage of the embeddings that I got from my variational autoencoder. So, first of all, what is variational autoencoder? First of all, it's a type of autoencoder. Autoencoder on itself is a type of neural network that tries to reconstruct some input signal from a small latent hidden embedding. So over here we see that we input to our network some object, then we shrink it to some small embedding, and then from this embedding we try to reconstruct our input object. The difference between variational autoencoder and simple autoencoder is that a variational autoencoder tries to model not just train data set in general, but it tries to find some underlying distributions in the data set. So what works were done in the last 15 years in this area? First of all, the first attempt to use autoencoders to represent some images, to encode some images, was done by Geoffrey Hinton and his student and his students. Then after that, autoencoders were generally used for image encoding, and the attempts to encode speech features were made in those two following works. For example, unsupervised speech context embeddings, and also work by Ordaron and et alias about a special type of variational autoencoder as a type of a generative neural network that was presented on Neuralips. So what problem were we trying to solve during this project, during this work? We tried to generate compressed spectrogram representations of some areas of speech based, we processed it through a convolutional variational autoencoder. We trained such dataset on this autoencoder to retrieve and the encoder part, the trained weights for the encoder part of the autoencoder, so that we could use the latent embedding, the embedding of the encoder to input to, for other tasks, for example, for speech recognition tasks. What dataset was used in this work? It was a subset of LibreSpeech. Overall, it had some 4,000 samples of train and 174 of test. These samples contained 1,030 speakers for train and 40 for test. Also, it's worth mentioning that the audio was converted to monochannel with sampling rate of 16 kilohertz, and all of these features were also implemented. Also, each utterance from the 4,000 and from the 100 from train and test was split into fragments of 300 milliseconds with stride of 100 milliseconds. This was our dataset for the variational autoencoder. So what were the parts of the neural network? First, it's the encoder that I talked about. You can't really see here, but the general idea is that we try to train the encoder and decoder, and we try to reduce our dimensionality of the data from 6,000 features to just a vector of 40 features, from which we then try to reconstruct again 6,000 features. The results were the following. So this part presents the original parts of speech, parts of the spectrogram, and these are the reconstructions. So in general, you can see that the form is preserved, although there could be made some changes, some changes to the forms, but in general, they are more or less the same. And those were the results when we applied our encoder of the neural network towards a speech recognition task. Basically, we used it as MFCC features, which some of you may know. MFCC features are the traditional features for speech recognition. And here we used an encoder part of variational autoencoder to encode parts of speech with stride, 300 milliseconds of speech with stride 1,000 milliseconds. So this experiment was carried out on Google command dataset, and the neural network that was trained for the command recognition was a simple multi-layer perceptron. So here we can see the results. What are the results? Is that our test accuracy is the same as in VCC, but in all of the other points we win, and that is the training time of multi-layer perceptron, then the best epoch that was reached, well, the value is lower, and also the train size is the size of our features that were stored on disk. They are 3 times as less. So those are the takeaway points from my talk. First of all, using this approach, audio information was well, it consumes 3 times less memory space on hard drive than basic MVCC features. Also, a multi-layer perceptron, multi-layered neural network trains 1.5 times faster, and also although we win in those points, we do not lose in accuracy compared to MVCC features. That's all. Thank you for your attention. If you have some questions, I'll be happy to hear them and answer them.
Are you sure?
Too hard.
So, as I understand, is this your master's thesis, right? Like
it's
future
my coursework.
Okay, so in future, as I understand, you're trying to use such approach for feature representation, and as I understand, this approach is not about accuracy at all. So we're just trying to not lose an accuracy, trying to compress our data, and after compressing, we get faster training. That's it.
First.
So the question is that will you try to somehow upgrade this solution for better accuracy?
Well, first of all, when this project started off, we hope that it would be better in all of the parameters, in all of the metrics. It wasn't very clear actually what this project will get us to. So in process, yes, it came out that the accuracy is the same, but the time consumed and the memory consumed, it is much lower. I think in the future there are reserves. There are many ways how this technology could be improved. So yes, I think in the future we will try to make the accuracy better, and I guess maybe for the end of the next year. But even in this realization, I think it could be useful, for example, for data storage, maybe for some voice banks, for voice databases that are then used in machine learning applications. So, yeah. Thank you for your question. Thank you.
Hello everyone. Today I'm going to present you my master thesis. So the theme of my project is automatic correlation of well logs using machine learning methods. My name is Kurochkin Eugeniy and my scientific advisor is Anton Luchkov. So to start with, let's answer these three simple questions. The first question is, what is geophysical methods of research? And the physical methods of research is a subsection of geophysics that studies upper layers of Earth in order to find mineral deposits such as oil and gas and others. So how do they study upper layers? First, they need to drill a well, and after that they move down a special device that's called logging probe and measure some physical quantities. And what quantities do they measure? Devices measure such quantities as density, porosity, radioactive radiation, temperature, and others. As a result of well logging, we obtain well logs, and on this picture we can see how it looks like. It represents the dependence of some physical parameter on the depth. In order to make a geophysical interpretation of well logs, we need to link them. And on this picture, we can see how this procedure looks like. We need to find peaks, and after that, connect peaks of one curve to peaks of another curve. Currently, we have problems with with log curves linkage because it has to be done manually and takes a lot of time resources. So we have two problems. The first problem is that we need to link different log curves of one well. We need to link them to have the ability to predict what kind of rock is on a certain depth. And the second problem, we need to correlate different wells of one deposit to have the ability to trace one formation where in investigation deposit. So we need to construct an algorithm that will predict for arbitrary depth point whether it is a peak point or not. To solve the formulated problem, we proposed 4 methods based on CNN, LSTM, BLSTM, and gradient boosting, and also we proposed 2 post-processing techniques that help us improve predictions after of prediction of algorithm. As far as we don't have real data, we need to generate it. So the generation consists of 4 steps. The first step, we generate the main part of the signal. It looks like the first picture. Then we generate peaks or benchmarks, and after that it becomes the second picture. After that we smooth the signal and add Gaussian noise. And finally we get something that resembles a real signal. So after that we need to prepare data for algorithms. For neural networks approaches, we don't use any additional features. For gradient boosting approach, we use features like average, standard deviation, dispersion, minimum, maximum module, and median value in the window of fixed width. And the width of the window is parameter. To evaluate the quality of proposed algorithms, we are going to use these two metrics. The first metric represents how it looks like F1 score, but in terms of peaks, where the peak is a group of consecutive points with label 1, and it may contain points with label 2, but they need to be single and separated. We are going to conduct two experiments. The first experiments will show us how changes the quality of prediction in terms of proposed metrics with increasing height of background signal. And the second experiment will also show us how changes quality in terms of proposed metrics, but with increasing the minimum peak of the minimum width of the peaks. And also we will cover the points how Gaussian noise affects the quality of prediction and how post-processing techniques can help us improve the quality of predictions. So on these pictures presented the best approach, it was CNN, and the second best was BLSTM and LSTM, and the worst was gradient boosting with window width of 5. On these pictures we can see that in all cases increasing of Gaussian noise decreases the performance in both metrics. And post-processing techniques help us to gain up to 2 or 3% of accuracy in case of CNN. In case of LSTM, it helps us up to 10%. This is experiment 2. And here we can see also that Gaussian noise affects the same way, but when we increase the minimum peak width, we have improvement. So was proposed 4 approaches for the problem. Proposed 2 quality metrics. Chosen the best approach, it was CNN. Proposed 2 post-processing methods, and in some cases it helps us to gain up to 10% of accuracy. And conducted experiments on how Gaussian noise affects the predictions. In all cases, it decreases the performance. That's all.
Добрый день, спасибо за доклад. Oh, sorry, forget to switch languages sometimes. Thank you a lot. Could you please describe how you were getting from the real data to the generated data, and why it is kind of more or less representing the real dependencies, real kind of behavior of data.
Mm-hmm. It's easier because real data costs money and we don't have it.
No, I mean.
So that's why we generate it. And as geologists say, it resembles the real signal.
Okay. Yeah, I get it.
I have one notion, maybe two. First, it's better to turn to the audience when you are speaking, because you are speaking to the desk. Second, it's better to place a number of slides.
Mm-hmm.
Okay. And third is when you draw pictures, place scale fonts maybe twice, because it's not readable. And for previous slide, can you turn? Yeah.
Так, я выключил.
Yeah. Yeah, it's not obvious. F1 for first is F1, for second F2. To show what the experiment is the same experiment. You just measure two different metric. Yeah.
It is an experiment number 2. Then I said on the previous
and you
slide.
measured F1, F2,
Yes.
and F2. Yeah, it's not not readable. Yeah, actually.
Mm-hmm. Mm-hmm.
Yeah. That's all. Other questions? No.
No questions?
Неудобно. Да, шаточки. Good evening. My master thesis is automatic facies classification from well-logs data using machine learning algorithms. My scientific advisor is Anton Zubkov. Так. Куда нажимать?
Чтобы переключать?
Да. Ага, это не работало. In oil and gas industry, in order to search and explore hydrocarbons, where boring is used. One way to study geological section is to select core rock sample and study it, but it is difficult and expensive. Some physical and chemical properties can be studied directly in the well by logging. Logging results in such diagrams of changing of physical and chemical properties of rocks along wells. According to these diagrams, professional geologists conduct lithological analysis, but this task is time-consuming and laborious and must be automated. So we have mathematical formulation of the problem. We have a set of object descriptions, set of classes, faces, finding training data, and must construct an algorithm that will able to classify any arbitrary object. For test and training data, I use data from online competition. It is a real data from 10 wells from Gugaton gas field, Kansas, USA. 7 properties were measured in these wells in different depths. There are 9 possible facies. Total amount of data is 4,150 objects. For one property, for the electric effect, we have about 66% of gaps. The data from different wells are very different from each other in number of depths, where properties were measured from 141 to 930, and in number of possible facies from 1 to 9. At first, in all experiments, I divided the initial data in test and training set in 2 different ways. The first one is splitting data in a certain proportion. The second one is separate one well for test. The first option is standard for data science, and the second option is due to geology. All experiments I conducted in 2 different conditions, with replacement of gaps by mean value and without the property with gaps. The accuracy of algorithm was measured by F1 score. At first, I have conducted experiments with simple classification algorithms, like naive Bayes classifier, decision tree, support vector machine, logistic regression, and others. In this stage of research, I have made the following conclusion. Results of testing on separate well is much worse than in splitted data. Replacement of gaps by mean value gives us better result, and the best algorithms for this problem, the best simple algorithms, are support vector machine and decision tree. In further experiments, I tried 2 variants of simple algorithms compositions by gain boosting. On this stage, I didn't choose the leader, but boosting on SVM shows extremely bad results and will not be considered later. In further experiments, I have considered 8 options of data augmentation. Each data augmentation has the main idea to display rock stratification and features. It was made by adding the information of properties of the previous and the next object in feature with different transformations. I have conducted experiments with 3 algorithms of compositions that was considered above, and the best result give decision tree boosting on decision tree with data augmentation the following. At first, we make a vector V from current object properties and difference of next and current objects properties divided by 0.5. And then make the feature vector from mean value of vector V from previous and current object divided by 2, properties of previous, current, and next objects, and mean value of vector V for current and next object divided by 2. The first stage of research, I started with analysis of classes correlation. I have introduced the concept of correlation. It is a number of permissions of class Y1 and Y2 that makes boosting on decision tree divided by the total number of objects of classes Y1 and Y2. And also define 4 degrees of correlation. This is the table of classes correlations with no data augmentation. There are 4 pairs of classes with correlation of degree 3, 4 pairs of classes with correlation of degree 2, and 11 pairs of classes with correlation of degree 1. Here's a table of classes correlation with the best data augmentation from previous results. And here we can see that the correlation for classes 1 and 2 was reduced from degree 3 to degree 2. And for classes 7 and 8 was reduced from degree 2 to degree 1. Also, for most pairs of classes, the correlation was reduced inside the same correlation degree. Because of data augmentation for objects that is located not in the boundary of layer, we have additional information of the same desired rock. And it helps us to improve the results. But for objects that is located on the boundary of layer, we add information about another class, which can differ a lot. It can make the algorithm choose a wrong feature to divide objects on groups and diminish the ability of algorithm to distinguish two similar classes. In order to avoid this effect, I propose the following algorithm. First step is to divide classes into two groups, and the classes from different groups must correlate it as weak as possible. Then classify the initial data on these groups, and it is important to this classification has accuracy close to 100%. And then for objects for each group separately, use data augmentation and then classify using gradient boosting algorithm on decisions. In my case, I have two groups of classes, and the accuracy of classify the initial data onto these groups is greater than 98%, and the final result is better than the previous result by around 2.5%. And this is the table of classes correlation after proposed algorithm. The correlation for classes 1 and 2, and 2 and 3, and 5 and 6 was reduced. Thank you for attention.
Thank you again. Could you please get back to the slide 44, I would say, 2 slides back. 2 slides back.
2 slides. This?
Yeah, here.
Okay.
You mentioned that accuracy on splitting onto groups was 98.5%. And how this accuracy was measured? I mean, on the train data, or you split it some test data?
I take initial data, then for that I have classes. If it's from first group, I make class 0.
Yeah, I get it.
And 1 and.
And I mean, have you split it then to the test and train and measured?
Yes,
okay, it is measured on test data.
Yes.
Okay,
yes.
and if you check that the initial train data was split with 100% accuracy, I mean, if the vector space you created is separable due to these two classes?
Yes.
Okay, good. Thank you.
Thank you for the nice presentation. And I have a couple of questions. First of all, when you showed in the first part of the presentation, when you had 2 different cross-validation scheme, and one was just a train test split, 60-30,
yes.
and another one was something like leave one well out. So
Yes.
you were leaving out one well, and you got different results on those cross-validation schemes, right?
Yes, but after receiving the result that the separate test well gives us much worse result, in order to make the problem closer to real situation, when we have a new test well and we must classify these rocks, in further experiments, I use only separate well for test.
Okay, so I'm not sure what do you think about that. Is it because the rocks from one well, from the same well, might have some kind of batch effect that gives effect on the accuracy estimation?
It's because of difference of wells.
Yeah. Okay. And then so for this part in the end, how equally well all classes are represented? Do you have approximately the same number of cases per each class, or what's the distribution of number of cases per class?
It's also a different statistic for each class, but there are no classes which differ from another's a lot.
Okay, thank you.
Some question from audience here.
Actually, we have the questions, and I'm not sure for whom it is. It's addressed for Alexandra or for Eugeniy, so I suppose that you have to answer it both. So the question is about one more question about your data from Julia. Have you compared other algorithms from other researchers?
Yes, I have compared my result, the results of this online competition. From that, I took the data and the results from first stage of experiments improved the previous results by around 2%.
Okay, and the next question, how can you be sure that you have sophisticated set of data? Actually,
I'm not sure.
Maybe it's more to Eugeniy question. And the previous question also. Do you remember?
Что это значит?
У тебя есть... У тебя были геологи, которые тебе помогали в этом разобраться? Нет, ты не ответил.
As I said before, my scientific advisor, as far as he is a geologist, he said that this data is quite sophisticated. There were no algorithms exactly on this problem, but I considered the approaches that other researchers used in quite similar problems, like classifying the sequence of objects. That's all.
More questions to Alexandra?
Thank you for your speech, and I have a small question. You tell us about boosting on support vector machines, and what kind of boosting do you use in this case? It was ADA boost or gradient boosting or
XGB boost.
Gradient boosting on support vector machines. And how do you realize this variant of boosting, gradient boosting, for support vector machines? What framework do you use for this thing?
From sklearn, I don't remember now.
In Sklearn, gradient boosting is developed for decision trees, not for support vector machines. You can use ADA boost on different types of classifiers, but gradient boosting in scikit-learn, gradient boosting was developed for only decision trees. And I have a question about support vector machines.
Yes, I don't remember, but I think it was AdaBoost. No, it was algorithm from sklearn where I can put another simple algorithm.
Okay, thank you.
Hello, everyone. My master thesis is generating high-quality synthetic speech using a generative adversarial network as workload pre-processing. No. Okay, table of contents. For the introduction, architecture, results, and reference. M is producing high quality synthesized speech. And the problem, the generated spectrograms are too over smooth. Here, why we use spectrograms? Because in a traditional TDS system, usually contains two parts. The first is text front end text analyzer, and the second is a speech synthesizer. Both of them contains many specific domain modules. Recently, TDS approach better on deep learning have been proposed and extensively integrated. Deep learning can integrate the front end and the back end into a single model, usually called as end-to-end learning, like Tagatron 2 and Clarinet. Those end-to-end generative text-to-speech model typically performs two steps. The first is to directly map the text to time-aligned acoustic features. Second is use a workload to convert the acoustic features to waveform. It has been found that spectrogram is reasonable and effective for the use of speech synthesis system. Therefore, we use spectrogram to bridge the two steps in a TDS system. For why over smoothness, next slide. What is osmosis? Next slide I will show. This is a solution. Considering the rapid development of image super resolution, image super resolution, a question arises whether the method of super resolution image reconstruction can be used to improve the quality of synthesized spectrograms. Our contributions is to answer this question and combine the image super resolution image translation with the acoustic feature processing. In our work, we propose a novel model combine pixel to pixel HD and res unit. The further image is cost mirror spectrogram. This one is the original. Here we can the further is the osmosis. This image has more detailed information. This is a condition GAN framework. This is our input and our label. We feed our cost spectrogram to a generator and want to for the discriminator, and the discriminator will find, and so the generator will upgrade. So finally, it will generate like the label one. Here we propose to utilize the adversarial strategy to train res unit. Yeah, many unit convo block and in radio unit, and here is downsampling, upsampling. This helps us. This helps the model to restructure the image. We use for multi-scale discriminators, D1, D2, D3, D4. For to distinguish the real spectrogram from the generated one. The second is SIM, is structure similarity index metric. This is a state-of-the-art perceptual metric to measure image quality. Provide sensitive to structure information and texture between this value between 0 to 1. For MSE, mean squared error. This loss function widely used for image restoration tasks. Find our full objective function include the part, and the alpha is a constant control the importance of those terms. We conduct commonly used mean opinion score test. Test to compare the result. We use 100 unseen causes merit spectrogram to generate the predicted merit spectrograms, and then use graphene and WebNet workcode to generate the audios. And those audios are sent to human rating service. The raters listen the audio and then give a marker. This marker is on a five scale. As we can see, our model has 0.44 improvement for graphene. For WebNet, 0.17. Both of them improve the synthesized speech quality, and the result also comparable to the original merit programs. Here, I guess maybe because of the workcode. If the workcode is better, maybe the score will be higher. Here are some samples. No. The further line audio was use graphene, and second use WebNet. And the WebNet is a very good workcode, but it takes generate 10-second audios need half hours. This is the input.
The instructions must be communicated to the local police in any event. It can be leaked to the press whether or not they are right. However, the instructions must be communicated to the local police in any event. It can be leaked to the press whether or not they are right.
No. Okay, finish. And I can wait. No. This is the reference. Any questions?
Thank you for your talk. I have the following question. What is actually the novelty of your approach compared to other researchers of GAN generation of audio?
Our contribution is like as we know, maybe we the first use the GAN and with generated audios. Like GAN can in image field has a very good result, but in audios not like image. The audio, if one sample change the audio very worse. But for image, one pixel change, we human can't see. And so we further combine the image translation with acoustic feature processing. And here we can see the improvement. 0.44 is a very huge improvement. And like around 80%. Here, this minus this minus this to divide around 80%.
Okay, thank you.
Just to note, in your presentation, please place on the last slide your publications. Yeah, okay. On SSDC and what publication on interspeech was sent.
Yes.
Not accepted, but sent to the interspeech. Okay.
Okay.
My name is Malysheva Anastasia, and today I'm going to talk about не было попроще конструкции. Как оно надевается? Не на мое ухо, это выемка. Можно микрофон, да? Меня смущают все эти конструкции. So, hi again. I'm going to talk about my master's thesis, which is the development and research of the prediction methods for time series obtained by the combination of different patterns. My scientific supervisor is Krichevsky. And let me begin with the problem description. Let us have sequence X1ST, which is generated from finite alphabet A. And the problem is to predict the most probable next unit of this sequence. In terms of real-time solutions, this problem is about forecasting behavior of any dynamic process. In fact, for this problem statement, most theoretical results are applicable if this sequence is generated by stationary and ergodic source. So we have different ways to deal with this problem, and all of them have some advantages and disadvantages. In fact, the best one for now, I guess, is a group of autoregressive models. And the main disadvantage is that they require some hyperparameters to be set by expert. And we will, in my master's thesis, I implement and research a special method which is based on Shannon information theory and universal coding. So the base of this algorithm is formed by a so-called Krichevsky predictor, which you can see on this slide. Here you can see a Krichevsky predictor for sequence A, for symbol A, to be generated if the sequence X1XT was generated before. On the bottom of this slide is an estimator for sequence X1XT to be generated like after some magic transformations. In fact, it is proved that such estimator is consistent for stationary and ergodic source. So then we can move for definition of Krichevsky measure for Markov source with finite memory M. And in my work, we will like move to this. We will work with this definition. There are several ways to define a probability distribution using this definition. One of them is R measure, which you can see on this slide. It was presented, I guess, 5 years ago. But as I said, we can use like any weight function in here. The main problem of such approach is that it requires exponential computation time. So it is not really applicable for real-time solutions. But about a year ago, it was presented a special algorithm to reduce this computation time to linear. And in my master's thesis, I like implement this algorithm and try to apply it to different problems. So first of all, as soon as we have only theoretical results on computation time, we've made a special experiment to understand the dependency between main parameters of algorithm and computation time. For this experiment, I've generated 100 random sequences for each sequence length and alphabet size like fixed, and made 50 units time series cross-validation. Then average computation time. As you can see on this slide, these are like only computation time because sequences are random. As you can see on this slide, we have a strict linear dependency between computation time and sequence length, and also computation time increases slowly when the alphabet size increases. So we can try to apply our algorithm to real like problems. So anyway, first of all, we need some pre-processing. As I said, our algorithm have some restrictions. And first pre-processing technique that we use for any time series that we get is we limit range of values if time series contains some kind of trend. So we just, instead of using units itself for prediction, we use the difference between the next unit and like the current one. That let us somehow limit the range of values. And to get the finite alphabet, we simply use finite partitions. It is obvious that using finite partitions decrease the like accuracy of our algorithm, but anyway, it is necessary for algorithm to work. And another problem is that the number of partitions is a hyperparameter of our algorithm. Then I've made some generation of data. I've made different like types of generators for different trends, seasonality, and also some kind of additive seasonality for each kind of pattern. Let it be pattern. I've generated 4 different data sets of fixed size, I guess 10,000 units for each. And so they differ like in several ways, for example, in periods, skew, range of values, and so on. And also random noise. I add some randomness to time series. Here you can see the results as a metric, as a evaluation metric. I use mean absolute percentage error. And also you can see that I sorted experiments on several time series. I sorted them on like my understanding how much the current time series differs from simple linear trend. So experiments are quite good. We have like the best results on exponential trend. It's quite obvious because after preprocessing, it's like quite similar to simple like linear trend. And anyway, on all the patterns, we see satisfactory results. So after that, we move to real data. We use real data sets to test our algorithm. And as data sets, I use exchange rate dynamics for August 2018. I pre-processed it, so instead of real values, I use like 0 or 1, depending on if rate increase or decrease. Also, we have a data set of minimum daily temperature from Sydney, Melbourne, Australia, and monthly sunspot data set. Also, I used some naive methods to compare. These are not like rocket science methods. It's just like to see the basics. Thank you. So these are methods that I used for comparing. And the results you can see on this table. I've measured accuracy, mean absolute error, and time. I used 100 units time series cross-validation. And you can see that, in fact, the amazing results I got on exchange rates, because it has like the smallest alphabet size. But also, despite the fact that our algorithm requires finite alphabet, it also shows significant results on MDDT and MST algorithm data sets, comparing with like some classical methods. So as a conclusion, I would like to say that I've implemented an efficient Krichevsky algorithm in my master's work. I've made some experiments on generated data. Also, I've made some experiments on real data, and both like types of experiments shows good results. And we have some popular patterns that are still good for our algorithm. Nice thing is that preprocessing technique, which is finite partition, shows good stability for random noise, which is quite obvious in fact. Some future plans for next month before my defense. I will implement 2 more models to compare results on generated and on real data. I will conduct additional experiments for time series made by combination of different patterns, because for now I have like solo ones. Then I've implemented a special technique for better performance in finite partition preprocessing, because for now, as I said, number of partitions is the hyperparameter of algorithms, and we want to move from this requirement. And I will prepare the source code for publication. Thanks for your attention. I'm sorry I forgot about references. If anyone wants, I can show you like the papers with the whole mathematics behind this solution. Thank you. Any questions?
Can you please switch 2 slides back? Yeah, what does it mean accuracy is 0?
The main idea is that accuracy like requires strict results, like strict equality. And this data set is real valued. So it's okay that accuracy is 0, because as a prediction, we have like the close value, not the strict one. And we still have like good mean absolute error, but 0 accuracy, that's fine.
It's 0, it means not 0. Accuracy means you calculate coincidence values. So what's the metric of accuracy here is mean?
Equality, like
equality.
Strict equality, yeah.
For float.
That's why I have 2 metrics: equality or accuracy and mean absolute error, because we have different data sets, and for some of them accuracy is a good metric, and for some of them mean absolute error is a good metric.
Okay, strange, very strange. It's you comparing float numbers by equality, yeah?
Yes. But only on these data sets. Only on this data set. More questions?
I could make not a question, but the notion that accuracy could be also measured with in the range.
Yes, but that's the idea, to measure it like strictly.
Oh, okay.
Thank you for the presentation. So follow-up question is then, does it mean that you want to use accuracy for integer time series and minimum absolute error for floating point time series data? Is that why you're using both of them for different data sets, or?
Kinda.
So if you're using equality, you want one integer to be equal to another integer, right? But
Yes,
so
yes.
is that what you mean?
In fact, as I said, the whole algorithm is made for like discrete values. And anyway, we want to understand if it is applicable for real values, like not theoretically, but in practice. And that's why we use both metrics.
Okay. And then so between the last three algorithms, the R measure and then different weights, so they're all your implementation of the same algorithm, but with different weights that you were showing on the one of the earlier slides.
The second one is like linear decreasing function, and the third one exponential decreasing function.
Okay. All right. Thank you.
Thank you.
Is it okay? So, hello everybody. My name is Juan Fernando Pinzon, and I'm going to talk to you about my scientific research project, my master thesis, which is sentiment analysis in social media texts for the Spanish language. My scientific supervisor is Anton Kolonin from the Institute of Computational Mathematics and Mathematical Geophysics. And this is the outline of the presentation. And okay, so let's start with what was the data source for my project. The data source for my project comes from the Steemit social media platform, which is a social media based on the blockchain technologies. So it was the whole post history is extracted by API. It's plus 50 million posts that include a wide variety of languages. I received this as a 14 gigabytes text file, and the data it's unlabeled. So first, my first task was to parse the data from this big corpus. So a parser was created to extract the Spanish posts from the source data. For that, a lexicon-based language classification was done, well, using a dictionary of more than 300,000 Spanish words. And with that, I was able to extract around 250,000 Spanish posts. So then, as I mentioned, the data is unlabeled, and manually labeling this amount of data is extremely time-consuming and expensive. So an automatic labeling approach based on emojis and emoticons was used. This based on positive results from the following publications. First one being sentiment expression via emoticons on social media. And are emoticons good enough to train emotion classifiers of Arabic tweets? Well, in this case, it's another language, but also proved to be successful. So this is what I obtained from labeling the data with the emoji approach, a highly imbalanced dataset, which gave me a 9.3% of positive posts, 90.3% of neutral posts, and 0.37 negative posts. So these high class imbalances produce confusing scores, meaning very high accuracy, precision, and recall, but very low F1 score, particularly the F1 macro score. So I started doing several type of tests, especially regarding the distribution of the classes. So I started making new data sets with different distributions. After several tests, I found that the distribution 177, meaning 1 negative post for 7 positive and 7 neutral, seemed to find show the best results. Trying to finding a balance between accuracy, precision, recall, and the F1 scores. I will talk to it about a little bit later. So regarding the architecture and the model used, well, it's neural networks, but for that, first we need to use some language models, word embeddings. And what's the need of using word embeddings? When we're dealing with raw text data, count-based models like bag of words and TF-IDF, that was what I was doing initially, are good, but they don't capture the whole semantic relationship among the words. So predictive methods like neural network-based language models try to predict words from its neighbors and try to learn the distributed representation producing dense word embeddings. So the first model was the word-to-vec model, the first of this type of embeddings. It was created in by Google in 2003. It's a predictive deep learning based model that computes and generates high-quality distributed and continuous dense vectors of words, which capture the contextual semantic similarity. So here we have a visual depiction of the skipgram word-to-vec model implementation. This left side picture, we see this skipgram that for this case, it's using a window of 2. So we have, the word, and for a window of 2, we're trying to understand the context, where here we're looking the 2 words previously and the 2 words ahead. And these are the inputs for the small neural network model that is just a 3-layer neural network that receives 2 inputs, one being the target word and the other inputs being the context words. So the small neural network here for the word-to-vec is an embedding layer, then a merge layer because we have 2 inputs, and then a dense layer that its activation function is a sigmoid, so we will obtain a statistical value. The second model used for word embedding was the fast-text model, introduced by Facebook in 2016 as an extension and supposedly improvement of the word-to-vec model. Instead of feeding individual words, this model what does is break the words in several n-grams, meaning smaller words. And finally, the GLOVE model, that's the global vectors for word representations algorithm, and it's an extension also to the word-to-vec method. And it was developed by Pennington and company at Stanford, and the GLOVE is an unsupervised learning algorithm for obtaining vector representation of words. Training is performed on aggregated global word-to-word co-occurrence statistics from the corpus. So what I found during using these 3 embedding models was first, word-to-vec and fast text models were implemented and trained using the GenSim Python library. Pre-trained GLOVE embeddings were used that were based on the Spanish billion word corpus. Fast text proved to be faster than word-to-vec. Word-to-vec showed slightly better performance, around 2% than fast text. GLOVE showed a slightly performance than word-to-vec. For the training of the vectors, for word-to-vec and fast text, I used embedding dimension of 256 with a window of 5. And this is the final architecture I use for my model. That is it's a convolutional neural network by LSTM deep net that it starts with 3 convolutional 1-dimensional layers, followed by a max pooling layer, then by LSTM, and 4 dense layers, each one of those with a dropout layer. And this is a model I found that apparently it gives really good results, especially for sentiment analysis. It's a very deep neural network, and as I mentioned, it gives really good results. So these are the results obtained with this model. As I was mentioning before, here are the comparison with the unbalanced data set. As I mentioned, 90% neutral, 0.3% of negative, and 9% of positive. This is the scores I get. As you may see, the accuracy, precision, and recall are really high scores. But if we take into consideration micro and macro scores, especially the macro score, look, is really low. As I mentioned, the one negative for each for 7 positive and 7 negative class distribution it showed to be a really good trade-off of accuracy, precision, and recall, but at the same time obtaining much better F1 scores. So here we may see this a little bit clear. The blue line represents the micro, F1 micro, and the red one, macro and micro for the unbalanced. So as you may see, there's a huge gap in the scores of these scores, in the values of this scores, sorry. And in the right side, we can see how it's for the 177 class distribution. We see that the values are much closer together. And as I was mentioning, well, there was a trade-off with the accuracy and precision and recall. For this case, this graph is showing the accuracy trade-off, the blue line being the unbalanced and the red one being the 177 class distribution. So it's trying to find the right balance. And this is a detailed presentation of the results obtained for each of the word embedding models, the word2vec, fast text, and GLOVE. As you may see, the word2vec is a little bit better than the fast text, and at the same time, the GLOVE is a little bit better, obtain better scores than the word2vec. And the best scores that I obtained with the 177 class distribution and the GLOVE embeddings are these ones. That's it. These are the list of references. Okay. That's it. Sorry. Someone has any questions? Okay.
Thank you for your speech. And I have some questions. You tell about automatic labeling your dataset using some emoticons, etc. But in this way, we can create a silver standard of dataset. Our labels maybe noisy. And for final, I think that for final testing, we have to use manual labeling, for example, using Mechanical Turk or another crowdsourcing framework for creation small but good labeled dataset. And this dataset we can apply for final testing of our trained algorithms.
Okay.
Do you think about this approach, about manual labeling for correct final testing?
Well, actually, I want to, but I've been keeping it, like, postponing it, because trying to find this approach with my scientific supervisors, we wanted to see the scores. Now, if in this last month I've had the time, I want to do it because especially my native language is Spanish, so I can do part of the manual labeling. And well, and regarding to that question, I wanted to ask you, what size do you recommend for a small data set to manual label by me? What size do you think should be enough?
We don't use this manual label dataset for training. We
for
will
last
use
validation.
only for final testing. And I think that size of such dataset can be 100 or 200 labeled texts,
Okay.
not hundreds of thousands.
Yeah, if it's such quantity, I can do it in 1 weekend. I can manually label, and it will be really good for validation.
Okay, thank you. And what about comparison with other more contextual embeddings of text? For example, universal sentence encoder or BERT models for more deeper and more contextual embeddings?
I tried with the Elmo embeddings. Unfortunately,
Elmo embedding is a good embedding for representation of words in text, but we can use OLM fit or universal encoder or BERT for representation of whole text as fixed size vectors.
Okay, actually, I read about the universal sentence encoders. I haven't tried the implementation yet, but I want to do it if I have the time in this last month to include it also here with comparison with these models.
Thank you.
Thank you very much.
Thank you for your speech. I have a question. How did you choose these specific data sets? What's the what's the specifics of this forum? And don't you think the distribution of negative and positive reviews sentences could be
based on the
reason
source?
could be because of this forum specific?
Yeah, actually, it might be. The idea behind choosing the Steamed social media instead of Facebook or Twitter is that when discussion with my scientific supervisor, knowing that this Steamed social media runs on top of the blockchain technology, it rewards the people that post and share interesting information with cryptocurrency. So in some way, you're getting paid for putting good content. So we thought that it was like a way to filter such such garbage text found in, for example, Twitter. Yeah, obviously they are very emotionally rich text, but this Steamed, we thought, and the logic behind it was that it is much moderated, and people try to do better posts, not just to blow some steam and just comment without thinking what's going to happen. Just this provides some like a more robust source. But yeah, you're right. Maybe if we try with Twitter or Facebook, we can get much more balanced in sentiment for the classes. It would be interesting for the future.
Thank you.
You're welcome.
Thank you for your presentation. So do you have in mind a specific task that would you be trying to solve using your method? Because it's interesting that you're focusing on improving the macro averaging of F1, because that basically means you don't care for which class you want to improve the classification, you just want it to perform globally equally for everything, right? Which is kind of a weird measure to optimize in practical way, because for practice you usually want to find the negative stuff or you want to find the positive stuff, or do you have some kind of application in mind for which you think this is a good way to develop the method?
Okay, well, for application itself, well, the project was conceived as an exploration of the techniques for social media unlabeled data. As you mentioned, I am trying to optimize the F1 score because there's no real application at the moment, but the idea of improving the F1 score is that the robustness of the whole algorithm itself is going to improve. And given a particular case we needed for better catching negative sentiment, we can just fine tune it or switch the distribution of the classes to get better according to
I think because you fix the imbalance by manually providing selecting the proportions of the classes, right? So if you want to take that method and then implement it and use it on a real data, it might not perform as well as on your synthetically produced proportions, because real proportions are going to be different from what you're doing, right?
Okay.
Thank you.
Thank you.